The dawn's first light reappears following the sun's passage. Visualize this. You're enveloped in the dimness before sunrise. Your exhalations are visible against the chilly November atmosphere. A telescope is aimed towards the eastern edge of the sky. The heavens possess that profound, deep blue hue that precedes the sun's arrival. While stars still twinkle, the sun's ascent is assured. And there, a mere 16 degrees from where our star will soon manifest, is a subtle glimmer that has journeyed through eons to reach this precise instant. 3 Atlas has returned. If you're viewing this broadcast presently, I have a request. Please tap the like button and subscribe to this channel. We're delving deeply into the most recent advancements, and believe me, you'll want to stay informed about what's on the horizon. Also, leave a remark indicating your location, the current time there, and most crucially, have you attempted to locate 3i Atlas yourself yet? I'm eager to learn if any of you have successfully captured this celestial traveler with your personal equipment. October 31st, 2025, a night of Halloween revelry. While the majority of the planet was occupied with costumes and confectionaries, astronomer Chi-Chang Zhang was engaged in a far more exhilarating pursuit. He was, in essence, resurrecting 3i Atlas from obscurity. Not literally, of course, but after the comet was obscured by the sun's overwhelming brilliance for nearly a month, Zhang successfully obtained what is considered to be the inaugural photographic record post-perihelion of our visitor from another star system. Employing the Lowell Observatory's Discovery Telescope in Arizona, a substantial 4.3-meter instrument, he managed to capture an image of the comet while it was still perilously close to the sun, just above the horizon during the early morning twilight. Contemplate the level of precision required for a moment. The comet was approximately 16 degrees distant from the sun. To provide some perspective, if you hold your closed fist at arm's length towards the sky, that represents roughly 10 degrees. Therefore, we are discussing a span less than 2 fist widths from the blinding radiance of our star. The sky was not yet fully dark. This was the period of morning twilight, that delicate interval when celestial bodies are still discernible, yet the sun is already commencing to suffuse the eastern sky with light. A single misstep, a fractional miscalculation, and the telescope could have been directed too near the sun, potentially compromising sensitive apparatus, or simply being overwhelmed by reflected solar illumination. However, Zhang's efforts did not cease there. 2 days hence, on November 2nd, he accomplished something that sent waves of excitement through the community of amateur astronomers. He photographed 3 Atlas once more, but this time utilizing a compact 6-inch telescope, a 152mm Ritchie-Frettian reflector. This was not an instrument costing millions of dollars at a research facility. This was the caliber of telescope owned by dedicated amateur astronomers, the kind that can be transported in a vehicle, the kind that resides in backyards across the globe, and it proved successful. The interstellar traveler was clearly visible, a faint, hazy disk against the backdrop of stars. The implications of this are profound. For the first time since 3 Atlas vanished behind the sun in late September, observers with everyday equipment can now detect an object originating from a different stellar system. You do not require access to the Hubble or Webb telescopes, nor to a colossal ground-based observatory. What you need are clear skies, an unobstructed eastern horizon, and a respectable amateur telescope. Zhang himself informed journalists that the comet would not appear spectacular, merely a vague smudge, but it would be a progressively discernible smudge in the ensuing days. This sense of accessibility, this democratization of celestial observation, is truly remarkable. This is no longer solely a scientific occurrence. It is something that belongs to anyone willing to awaken before dawn and direct their telescope towards Virgo. The timing of this reappearance is of paramount importance. 3i Atlas reached its perihelion, its closest proximity to the sun, on October 29th. At that juncture, it was approximately 203 million kilometers from our star, roughly 1.36 astronomical units. For comets, perihelion represents the moment of peak drama. The intense solar radiation heats the nucleus, causing volatile ices to transition directly from solid to gas, thereby generating the characteristic coma and tail. It is during this period that comets are typically at their most luminous and active. However, therein lies the difficulty. From Earth's vantage point, 3I Atlas was situated on the opposing side of the Sun during this critical interval. We were unable to observe it. Ground-based telescopes were entirely blind to any events transpiring. This is where observatories situated in space became absolutely indispensable. While astronomers tethered to Earth endured frustration, instruments such as the Solar Terrestrial Relations Observatory, known as STEREO, the Solar and Heliospheric Observatory, designated SOHO, and even the weather satellite GOES-19 maintained their electronic vigilance on the comet. These spacecraft, primarily designed for monitoring the sun and space weather, found themselves tracking an interstellar visitor as it approached its closest point to our star. The data they amassed during those unseen weeks has proven to be some of the most unexpected and contentious information we have received regarding 3I Atlas thus far, but we will address that shortly. The re-emergence of 3 Atlas in early November signifies the commencement of what astronomers are terming a crucial observation period. Zhang noted that the comet is rapidly ascending from the sun's position in our sky. Within a week of his initial imagery, the comet would be 25 to 30 degrees distant from the sun, rendering it accessible to larger telescopes globally. This increasing angular separation is vital because it translates to extended observation durations each night, darker skies, and diminished interference from scattered sunlight. The comet is progressively higher in the pre-dawn sky with each passing day, migrating northward from our perspective, thereby facilitating easier observation from locations in the northern hemisphere. But let us discuss what observers are presently beholding now that 3 Atlas is once again visible. The comet presents itself as a compact, faintly hazy white point of light. There is a concentrated central area, the coma, encircling the nucleus, and contingent upon the duration of the exposure and the aperture of the telescope, observers are reporting faint indications of a tail, not the majestic, sweeping tail associated with a great comet, such as Halley's Comet, or even more recent visitors like Comet Leonard. 3 Atlas is considerably more understated. Its luminosity is estimated to be around magnitude 9 to 10, which positions it well beyond naked eye visibility, but comfortably within the reach of binoculars and modest telescopes under dark skies. For context, the faintest stars perceptible to the unassisted eye under ideal conditions are approximately magnitude 6. Each increment in magnitude signifies a reduction in brightness by a factor of approximately 2.5. Consequently, magnitude 9 is roughly 16 times less luminous than what your eyes alone can perceive. The conditions for visibility are improving daily. On November 9th, the comet attained an elevation of 10 degrees just prior to the onset of dawn for observers situated at 40 degrees north latitude, which approximates the latitude of cities such as Denver or Philadelphia. The moon was in its waning gibbous phase, presenting certain challenges for visual observers due to the bright moonlight obscuring faint objects. However, by November 16th, the comet's altitude had doubled to 20 degrees, and the moon had become a slender crescent positioned a mere 4 degrees south of the comet. From November 16th through approximately December 2nd, the moon will essentially be absent from the sky, providing optimal dark sky conditions as 3 Atlas ascends through the morning sky, traversing the constellation Virgo. There are some notable celestial conjunctions on the horizon for those tracking the comet. On November 18th and 19th, 3 Atlas will pass 1.5 degrees south of Gamma Virginis, also known as Porrima, a second magnitude star that will serve as an excellent reference point for locating the comet. On November 22nd, it will have a close encounter with the 13th magnitude galaxy, NGC 4454. Such alignments are invaluable opportunities for astrophotographers. Envision capturing an interstellar comet originating from a planetary system billions of years old, transiting in front of a galaxy comprising hundreds of billions of stars, all within a single photographic frame. It is a cosmic perspective that profoundly illuminates our place within the universe. Zhang's imagery also revealed another significant aspect. The comet might still be increasing in brightness. The data suggests that 3 Atlas may not have yet reached its peak luminosity, even subsequent to perihelion. This is an atypical, though not unprecedented, occurrence. Certain comets continue to brighten for days or even weeks after their closest solar approach, as previously frozen volatiles deep within the nucleus finally attain sufficient temperatures to sublimate. Whether this ongoing brightening is indeed occurring with 3I Atlas necessitates further data. More observations from diverse locations and instruments are required. However, the prospect is intriguing as it suggests the comet could become even more readily observable than initially projected. The role of the Lowell Discovery Telescope in capturing these initial images cannot be overstated. This is one of the few large telescopes globally capable of orienting itself sufficiently close to the horizon to observe celestial objects shortly after their emergence from solar conjunction. Most prominent observatories impose restrictions on how near they can point to the horizon due to atmospheric turbulence, light pollution from nearby urban areas, and the inherent physical limitations of telescope mounts and domes. The Lowell telescope, situated at an elevation of 2,360 meters in northern Arizona, benefits from relatively dark skies and a mount engineered for enhanced maneuverability. Zhang exploited this narrow window of opportunity, that fleeting period when the comet was above the horizon, yet the sun remained sufficiently below it to permit imaging, thereby securing these historic photographs. Consider the transient nature of this chance. Had Zhang delayed even a few more days, other observatories might have achieved this feat before him. Had he attempted it a few days earlier, the comet might have been too proximate to the sun for safe observation. This caliber of astronomical endeavor demands not only access to potent equipment and clear skies, but also impeccable timing and a willingness to undertake calculated risks. Zhang reportedly employed a smaller 6-inch telescope for experimentation and to assess conditions before dedicating valuable time on the more substantial Discovery telescope. Access to major research telescopes is exceptionally competitive and scheduled months in advance. Every minute holds immense value. Every observation must yield significant results. His preliminary work with amateur-grade equipment yielded spectacular outcomes. Now that 3 Atlas is once again visible, the scientific community is mobilizing. Observatories worldwide are incorporating the comet into their observing schedules. Spectroscopes are being directed towards it to analyze the composition of gases within its coma. Photometric monitoring is tracking its variations in brightness. Radio telescopes are actively listening for any emissions. Every piece of data collected at this juncture will contribute to resolving fundamental questions about this visitor from another star system. What is the composition of its nucleus? How does its makeup compare to comets, indigenous to our solar system? What insights into the molecular cloud where it originated billions of years ago can its chemistry provide? The European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, is slated to observe 3I Atlas in November, utilizing multiple instruments. Although JUICE will be positioned farther from the comet than the Mars orbiters were during the October flyby, it will observe 3I Atlas shortly after perihelion, when the comet is anticipated to be in its most active state. The data from JUICE will not be transmitted back to Earth until February due to the spacecraft's considerable distance and its data transmission rate. However, upon its arrival, those observations will furnish yet another perspective on this enigmatic celestial body. There is something profoundly moving about the return of 3 Atlas to our skies. For nearly a month, it remained concealed from our view, engaging in whatever activities comets undertake when bathed in intense solar radiation, unobserved by Earth. Now it has reappeared, perhaps altered by its encounter with the sun's heat, receding from perihelion on its hyperbolic trajectory that will ultimately propel it beyond our solar system indefinitely. This is not an object that will return in 76 years, like Halley's Comet, nor even in thousands of years, like some of the long-period comets from the Oort cloud. 3 Atlas is here but once. Every observation is consequential because there will never be another opportunity. Amateur astronomers globally are setting their alarms for the pre-dawn hours, venturing into the chilly November darkness, equipped with thermoses of coffee and celestial charts marked with the comet's predicted position. Some will succeed in capturing it. Others will face challenges with cloud cover, light pollution, or equipment malfunctions. However, they are all participating in a moment that will be etched in astronomical history. They are all observing photons that originated from that distant comet. Photons that traversed the inner solar system, penetrated Earth's atmosphere, and entered their telescope optics. Those photons carry information from another star system, encoded in their wavelengths and intensities, awaiting decipherment. Zhang's images, captured with both the Discovery telescope and his compact amateur scope, are now circulating within astronomical circles online. Social media feeds brimming with astrophotography are showcasing 3-Eye Atlas alongside imagery of galaxies, nebulae, and other comets. The interstellar visitor is becoming an integral part of the routine observing schedule for dedicated comet enthusiasts. Online forums are abuzz with reports. Captured it this morning at magnitude 9.5, utilized an 8-inch Schmidt-Cassegrain. 30-second exposures clearly visible in the stacked image. Attempted observation, but morning twilight was too bright. We'll try again tomorrow. This represents citizen science at its most exemplary. Professional astronomers with their multi-million-dollar instruments, collaborating with amateur observers, wielding their backyard telescopes, all contributing segments to the same cosmic enigma. The widespread accessibility of astronomy, facilitated by affordable imaging technology and the Internet, signifies that an individual in their driveway in suburban America might capture a detail or detect a sudden surge in brightness that complements data acquired by Hubble or Webb. The comet remains indifferent as to whether it is being observed by a Nobel laureate or a high school student with an ardor for the stars. It simply exists, traversing space, reflecting sunlight, and divulging its secrets to anyone who observes with sufficient diligence. As 3 Atlas ascends higher in the pre-dawn sky over the ensuing weeks, its visibility will continue to improve. By mid-December, when the comet achieves its closest approach to Earth, at approximately 270 million kilometers, it will be sufficiently elevated in the sky before dawn to permit extended observation sessions. This December proximity represents the final significant milestone in our capacity to study this object before it embarks on its flyby of Jupiter in March 2026 and subsequently departs our solar system permanently. The reappearance of 3-Eye Atlas after its solar conjunction is more than merely an astronomical event. It serves as a reminder that the universe operates according to its own immutable schedule, unswayed by our desire for observation. The comet vanished behind the sun because orbital mechanics dictated its trajectory. It reappeared when geometric conditions permitted, not a moment prematurely. And now, for a confined interval measured in weeks, we possess the opportunity to direct our instruments skyward and gather whatever intelligence we can before this visitor from the farthest reaches of interstellar space continues its perpetual voyage through the galaxy. The very fact that we can participate in this moment, whether through professional research or amateur observation, stands as one of the profound privileges of inhabiting an era where the cosmos is accessible to anyone possessing curiosity and a readiness to look upward. Kim Kardashian's influence extends to Congress. How 3IE Atlas became a viral sensation. Something extraordinary transpired during the final week of October 2025. An interstellar comet became the subject of tweets from reality television personalities, demands from members of Congress, and impassioned discussions across global social media platforms. 3 Atlas transcended the confines of astronomical journals and science news websites to emerge as a genuine cultural phenomenon. The critical question is, how did a faint speck of light in the morning sky capture the attention of millions of individuals who have never peered through a telescope? On October 31st, Kim Kardashian posted on X, formerly known as Twitter. Wait, what's the T on 3i Atlas? The tweet was unpretentious and colloquial, employing language readily understood by her hundreds of millions of followers. Within hours, it had garnered millions of views. NASA's acting administrator, Shaw Duffy, responded directly. NASA's observations indicate that this is the third interstellar comet to traverse our solar system. No aliens, no threat to life on Earth. A straightforward reply from the head of the space agency to one of the planet's most celebrated individuals, all unfolding publicly on social media. However, Kardashian's interest was not mere idle curiosity. The discourse surrounding 3 Atlas had been escalating for weeks within segments of the internet where conspiracy theories intermingle with legitimate scientific discussions. YouTube channels dedicated to unexplained phenomena had been producing videos with increasingly sensational titles. Forums on Reddit were filled with speculative commentary, and perhaps most disconcertingly, deepfake videos had begun circulating, featuring fabricated footage of respected scientists, such as physicist Brian Cox, seemingly discussing extraterrestrial origins for the comet. These were not crude alterations. They were sophisticated enough to deceive casual viewers, utilizing artificial intelligence to generate realistic vocal patterns and facial movements. Brian Cox himself addressed the deepfakes publicly, expressing concern not only regarding the misappropriation of his likeness, but also about the broader ramifications. "It doesn't matter so much if it's nonsense about a comet," he tweeted, "but in other areas of science and certainly politics, it's clearly important." YouTube eventually removed several prominent accounts responsible for the deepfake videos, but the damage was already inflicted. The narrative that 3 Atlas might represent something beyond a natural comet had escaped the confines of fringe websites and permeated mainstream consciousness. Enter Avi Loeb. The Harvard astrophysicist has become arguably the most contentious figure in the 3 Atlas saga, and his media appearances in late October and early November poured fuel onto an already blazing fire. On October 30th, Loeb appeared on Joe Rogan's podcast, one of the most widely listened to programs globally, with an audience measured in the tens of millions. The conversation spanned numerous subjects. However, when it turned to 3 Atlas, Loeb did not hold back. He critiqued NASA for what he characterized as a lack of transparency concerning crucial observational data. The specific issue Loeb raised involved images captured by the HiRISE camera aboard the Mars Reconnaissance Orbiter. These images were taken on October 2nd and 3rd when 3 Atlas passed within 30 million kilometers of Mars. According to Loeb, the HiRISE camera achieved a spatial resolution of 30 kilometers per pixel, approximately 3 times superior to the best publicly accessible Hubble images obtained in July. More significantly, these images offered a lateral perspective of the comet, invaluable for comprehending the geometry of material being ejected from its surface. But as of Loeb's appearance on the Rogan podcast, NASA had not publicly released these images. 4 weeks had elapsed since their capture. Loeb's explanation for the delay was blunt. When Rogan inquired if the holdup might indicate something unusual in the images, something NASA wished to conceal, Loeb dismissed the conspiracy angle with his characteristic directness. The delay is probably not a sign of extraterrestrial intelligence, but rather of terrestrial stupidity. He pointed to the government shutdown that commenced on October 1st as the root cause of the difficulties, asserting that scientific pursuits were being compromised by political discord. We ought not to subordinate scientific endeavors to the immediate political gridlock, he declared. The scientific community stood to gain significantly from the timely distribution of this time-sensitive information, as celestial cartographers were making preparations for subsequent observations in the months ahead. The appearance on Joe Rogan's program performed its customary function, amplifying Lowe's message to a demographic extending far beyond academic spheres. Rogan suggested that Lowe communicate directly with NASA Administrator Shaw Duffy. Lowe heeded this counsel, but he also initiated contact with an individual possessing potentially greater influence, Congresswoman Anna Paulina Luna. Representative Luna, a Republican representing Florida, had previously demonstrated an inclination towards investigating unexplained aerial phenomena and unconventional scientific subjects. She had questioned individuals during congressional inquiries concerning UFOs and had advocated for increased openness regarding scientific data held by the government. Upon Lowe's outreach regarding 3I Atlas, she responded with alacrity. On October 31st, coincident with Kim Kardashian's public query about the comet, Luna dispatched a formal letter to the acting NASA administrator, Shaw Duffy. The correspondence was notably forthright. Luna requested the prompt disclosure of the high-resolution imagery from the Mars Reconnaissance Orbiter. She specifically highlighted that these images possessed a spatial resolution of 30 kilometers per pixel, a level of detail comparable to the finest publicly accessible image from the Hubble Space Telescope captured on July 21, 2025. The letter underscored that this data held profound importance for advancing our comprehension of interstellar travelers and their interactions within our solar system. However, Luna's communication extended further. She also solicited any supporting information from Mars missions that might have registered anomalous activity in the vicinity of Mars during 3I Atlas's closest transit. This specific phrasing prompted curiosity. What precisely constituted anomalous activity? The letter offered no clarification, leaving ample room for conjecture and, inevitably, speculation. Luna further urged NASA to allocate resources for additional observations of 3I Atlas, utilizing the Juno spacecraft, which was currently orbiting Jupiter, employing all available instruments, including radio sensors. On November 3rd, Luna followed up with another public statement, this time directly addressing Administrator Duffy. Can you please review the letter below? We are eager to view images of 3I Atlas. She appended the complete text of her October 31st communication. The pressure was now public, visible, and emanating from an elected official possessing a significant platform. NASA's response was measured. Administrator Duffy's reply to Kim Kardashian articulated the agency's official stance. 3I Atlas is the third known comet originating from outside our solar system. It displays no characteristics suggesting it is anything other than a natural celestial body. It poses no peril to Earth. This represents a scientific opportunity, not an emergency. NASA's chief scientist, Tom Statler, elaborated further in media pronouncements, stating that 3I Atlas bore a very strong resemblance to known comets and dismissing theories concerning artificial origins. Yet, these assurances did little to assuage the ongoing discourse. Lowe retorted to Statler's statements in interviews with publications such as Lad Bible. A declaration from NASA or any other entity that definitively closes the discussion and discourages the airing of alternative viewpoints is truly counterproductive, as the public has a right to hear diverse scientific perspectives. He contended that proclaiming the matter settled without releasing all pertinent data was fundamentally at odds with the scientific method. The situation intensified further when journalist Christina Gomez published a comprehensive analysis revealing that Luna had, in fact, submitted two distinct letters to NASA concerning 3I Atlas. The initial correspondence, dated July 31st, proposed redirecting the Juno spacecraft to intercept the comet, citing Lowe's analysis that a specific propulsive maneuver on September 14th could position Juno for observations during 3I Atlas's March 2026 passage by Jupiter. The estimated expenditure for a 6-month mission extension was $15 million. This initial letter went without acknowledgement. The subsequent communication in October adopted a significantly different strategy, demanding the release of data NASA had already gathered rather than proposing novel observational efforts. This alteration suggested that Luna and her staff had come to the realization that the agency had been meticulously observing 3I Atlas, but was withholding its findings. The controversy drew the attention of other prominent figures. Elon Musk, whose relationship with space agencies is notably complex given his leadership of SpaceX, offered enigmatic remarks about 3I Atlas across various online forums. Technology influencers and science communicators found themselves fielding inquiries from audiences who had suddenly developed a profound interest in cometary orbital mechanics and spectroscopic analysis. The comet repeatedly became a trending subject as each new development unfolded. The particular potency of the 3I Atlas narrative stemmed from its amalgamation of several elements that strongly resonate within contemporary society. There is a prevailing distrust of governmental institutions and a vocal demand for transparency. There exists a tension between established scientific consensus and dissenting voices like Lowe's. The story possesses an inherent accessibility, featuring a visitor from another star system traversing our celestial vicinity. And crucially, there is an authentic enigma, the unresolved questions surrounding the comet's peculiar behavior, which even mainstream scientists concede. The emergence of deepfake technology introduced an additional dimension. In an era where artificial intelligence can generate convincing visual fabrications of individuals uttering any statement, the 3I Atlas saga served as a case study in the propagation of misinformation. The fabricated videos of Brian Cox were not the product of state-sponsored initiatives or sophisticated disinformation campaigns. They were created by individuals seeking online visibility and engagement, capitalizing on conspiracy theories through YouTube's advertising revenue model. YouTube's eventual intervention highlighted both the pervasiveness of the problem and the limitations of platform content moderation, when material can be produced and disseminated at a rate exceeding review capabilities. Social media algorithms serve to amplify all content. Posts concerning 3I Atlas that generated significant engagement, whether driven by genuine scientific curiosity or speculative conspiracy theories, were promoted to a wider user base. The more sensational the assertion, the greater its propensity for sharing. Unbiased scientific updates found themselves competing for attention against headlines purporting alien motherships or governmental cover-ups. Within this landscape, the actions of a congresswoman demanding data release and a Harvard professor questioning official accounts provided ample fodder for every conceivable interpretation. The scientific community found itself in an awkward predicament. Researchers who had dedicated months to meticulously observing 3I Atlas, authoring scholarly articles, and analyzing data were suddenly confronted with their work being discussed by millions, many of whom lacked any foundational knowledge in astronomy. Some welcomed the attention, viewing it as an opportunity to cultivate public interest in science. Others harbored concerns that the signal-to-noise ratio had become unmanageable, that legitimate inquiries were being overshadowed by sensationalism. Lowe himself became a focal point. His detractors, numerous within the astronomical community, accused him of seeking notoriety and promoting fringe theories to promote his books and secure funding for his Galileo project, which investigates extraterrestrial technology. Conversely, his supporters maintained that he was posing essential questions and challenging an established order that had grown too complacent in dismissing anomalies. The truth, as is frequently the case, likely resided in the nuanced space between these opposing viewpoints. However, regardless of intent, the viral phenomenon achieved certain outcomes. It compelled NASA to engage with public inquiries regarding 3I Atlas on a scale that would not have otherwise transpired. It drew attention to the critical importance of timely data dissemination in astronomy, where observational opportunities can be exceptionally brief. It demonstrated that the public possesses a vested interest in interstellar visitors, even those so faint as to necessitate telescopic observation. And it fostered a cultural moment where a comet, a celestial body composed of ice and rock from another star system, became a topic of conversation in everyday settings. The high-resolution images remained undisclosed as of early November. NASA has not provided a definitive time frame for their release. Scholarly papers examining 3I Atlas continue to appear on preprint repositories and within peer-reviewed journals. The comet persists in its journey through space, unperturbed by the human drama unfolding in its wake, and the fundamental question of transparency in scientific inquiry, particularly concerning objects that capture widespread public fascination, remains unresolved. Kim Kardashian's tweet, though seemingly a minor detail in this narrative, represents a significant indicator. When one of the most followed individuals on social media inquires about a celestial object, it signifies that the object has permeated the collective consciousness. Whether this is advantageous or detrimental to scientific progress is a matter of perspective, but its impact is undeniably considerable. 3I Atlas transitioned from a niche interest for comet specialists to a subject of discussion among hundreds of millions globally. Such attention presents both opportunities and challenges, and the manner in which the scientific community navigates this juncture may shape public engagement with astronomy for years to come. Amateur observers captured the interstellar visitor with their own equipment. There exists a profoundly egalitarian aspect to the night sky. A photon that has journeyed from 3I Atlas makes no distinction between landing on the mirror of the Hubble Space Telescope or the lens of a 6-inch reflector in a residential backyard. The underlying physics remains identical. The information contained within the photon's wavelength and intensity is consistent. And in early November 2025, amateur astronomers worldwide realized they had joined an elite cohort. They were capable of observing an interstellar object using their own apparatus. The moment Chi-Chong Zhang published his November 2nd image, captured with a 152mm telescope, ignited a surge of activity within the amateur astronomy community. Forums typically dedicated to equipment reviews and astrophotography techniques were suddenly inundated with discussions pertaining to 3I Atlas. Is it truly discernible with my 8-inch Schmidt-Cassegrain? What exposure duration is required? Can I observe it from my suburban residence, or is a location with minimal light pollution necessary? Questions poured in from observers of all proficiency levels. Within 48 hours, confirmatory images began to surface. An observer in Arizona, utilizing a Celestron 8-inch telescope, reported successfully capturing the comet clearly through a composite of 20-30-second exposures. An individual in New Mexico, employing a 10-inch Dobsonian reflector, shared a sketch rendered at the eyepiece, depicting the comet as a faint, circular luminescence with a subtle tail extension directed southwestward. A photographer in California combined 200 frames acquired with a telephoto lens mounted on a tracking apparatus, producing an image that not only showcased Three-Eye Atlas, but also several background galaxies within the same field of view. The accessibility of Three-Eye Atlas to amateur equipment signifies a relatively uncommon occurrence in contemporary astronomical research. The majority of celestial bodies that garner substantial scientific attention are far too faint for backyard telescopes. The detection and analysis of exoplanets necessitate the use of space telescopes and intricate analytical methodologies. While distant galaxies may be photographable by dedicated amateurs, their observation contributes minimally to professional scientific endeavors. Asteroid discoveries have largely been automated through comprehensive sky survey programs that operate with a thoroughness unattainable by any individual. However, Three-Eye Atlas occupies a particularly advantageous position. It possesses sufficient brightness to be captured with moderately capable amateur instruments. Concurrently, every observation contributes valuable data. Why is data acquired by amateurs significant for an object being studied by the world's most powerful telescopes? Professional observatories operate with finite resources and are unable to continuously monitor the comet. Sudden energetic bursts, fluctuations in luminosity, or alterations in coma structure could transpire between scheduled professional observation windows. Amateur astronomers, particularly those who are retired or possess flexible schedules, can undertake regular surveillance of celestial targets. They are capable of detecting changes that might otherwise go unnoticed. And with Three-Eye Atlas approaching its December closest proximity to Earth, continuous monitoring assumes considerable scientific importance. Consider the worldwide distribution of amateur observers. As the sun sets in Europe, it is already night in Asia and still daytime in the Americas. This arrangement provides virtually uninterrupted observation of the sky. Three-Eye Atlas ascends in the pre-dawn sky, enabling observers in different time zones to view it during distinct hours, thereby creating an observational relay that follows the Earth's rotation. An observer in Japan photographs the comet before dawn. Subsequently, an observer in Europe captures it a few hours later as dawn breaks there, followed by North American observers continuing the coverage. Professional observatories cannot replicate this geographical diversity and temporal coverage. The technical prerequisites for observing Three-Eye Atlas are relatively modest by astrophotography standards. The comet currently registers at approximately magnitude 9 to 10, meaning it is discernible through binoculars under dark skies, albeit appearing very faint and requiring precise knowledge of its location. A 4-inch telescope renders it clearly visible as a hazy patch, distinguishable from the surrounding stars. A 6 to 8-inch telescope, the workhorses of amateur astronomy, reveal the comet distinctly, exhibiting evident coma structure. Larger amateur instruments, 10 inches and above, can begin to delineate tail details and track subtle shifts in brightness. The imaging process demands patience, but not specialized or esoteric equipment. A tracking mount, indispensable for any deep sky astrophotography, maintains the telescope's alignment with the comet as the Earth rotates. A camera, either a dedicated astronomical device or a modified digital single-lens reflex camera, captures individual frames. Most observers utilize exposure times ranging from 30 seconds to 2 minutes, striking a balance between the necessity of accumulating sufficient light and the comet's movement across the sky. Subsequently, the process of stacking commences, involving the combination of dozens or hundreds of frames to mitigate noise and accentuate faint details. Software applications such as Deep Sky Stacker or PixInsight facilitate this post-processing, transforming a collection of noisy individual images into a refined final product. However, this is where Three-Eye Atlas presents a unique challenge. Unlike the process of photographing a stationary galaxy or nebula, The comet is moving at a comparatively rapid velocity against the backdrop of stars. Consequently, stacking software must be configured to track the comet's trajectory, not the stars. Some programs incorporate built-in modes for comet stacking. Others necessitate manual alignment, using the comet itself as the reference point. The outcome is that stars appear as elongated streaks, while the comet remains sharply defined. This is the inverse of what occurs when tracking stars while a comet drifts through the field of view. Several amateur observers have embraced this challenge and transformed it into an art form. Images that depict 3-Eye Atlas as a sharp point with radiating star trails surrounding it offer a visual representation of the comet's motion through our solar system. One photographer created a time-lapse animation using frames captured over a 3-hour period, illustrating the comet's movement against the stellar background in real time. These are not merely aesthetically pleasing images. They are tangible demonstrations of orbital mechanics brought to visual life. The communal aspect of amateur observation has been truly remarkable. The 3-Eye Atlas X account, managed by enthusiasts meticulously tracking every development related to the comet, has evolved into a central repository for amateur imagery. Observers tag their photographs, share detailed acquisition parameters, and provide constructive feedback on each other's work. There is an absence of competition here, no sense of vying for the superior image. Instead, a spirit of collaboration prevails. An individual who has successfully imaged the comet shares their precise settings, assisting others who may have encountered difficulties due to cloud cover or equipment malfunctions. Tips are exchanged regarding strategies for mitigating light pollution, managing dew formation on optical components during chilly pre-dawn observation sessions, and employing processing techniques to enhance subtle details. For a significant number of amateur astronomers, 3-Eye Atlas represents their inaugural opportunity to observe an object originating from beyond our solar system. The first definitively identified interstellar visitor, discovered in 2017, was far too faint for amateur instrumentation by the time its interstellar origin was confirmed. 2-Eye Borisov, discovered in 2019, proved more accommodating, reaching a brightness of magnitude 15 at its peak, rendering it accessible to experienced amateurs equipped with larger telescopes and imaging apparatus. However, 3-Eye Atlas surpasses Borisov in brightness, making it visible to a broader spectrum of observers. This increased accessibility carries significant educational implications. High school astronomy clubs are organizing pre-dawn observation sessions, providing students with the opportunity to witness an actual visitor from another star system through their school's telescope. Universities are integrating 3-Eye Atlas observations into undergraduate astronomy laboratory courses, instructing students on orbital mechanics, spectroscopy, and the scientific method while they study a genuine research target. Planetariums and science centers are hosting public viewing events, although the pre-dawn timing presents scheduling challenges. The observational conditions throughout November and December are progressively improving for observers in the northern hemisphere. The comet's elevation above the horizon increases each morning, offering darker skies and extended observation periods before twilight obscures celestial objects. By mid-November, 3-Eye Atlas ascends approximately 2 hours prior to sunrise at mid-northern latitudes, affording observers a comfortable observational window. The frigid November mornings contribute to excellent atmospheric transparency, a stark contrast to the conditions faced by summer observers who contend with haze and humidity. Winter air, while potentially uncomfortable for the astronomer, generally provides some of the clearest skies of the year. Observers situated in the southern hemisphere encounter different atmospheric conditions. The comet's trajectory and current celestial position favor viewers in the northern hemisphere, although it remains observable from southern latitudes, albeit with some difficulty. Observers in Australia and South America report the necessity of clear horizons and precise timing to capture the comet positioned low in the sky before sunrise. This geographical disparity in visibility has resulted in a concentration of observations emanating from North America, Europe, and Asia, although dedicated amateur astronomers in the Southern Hemisphere continue to contribute valuable data. Equipment reviews have acquired renewed significance as observers endeavor to optimize their setups for cometary observation. Which eyepieces offer the most advantageous views of low-surface brightness objects? Which camera sensors exhibit the greatest sensitivity to the specific wavelengths where cometary emissions occur? How do different telescope designs, such as refractors versus reflectors, influence contrast when observing against the backdrop of twilight skies? These discussions, typically abstract in nature, now possess a concrete practical application. The answers to these questions hold importance because observers are keen to witness Three-Eye Atlas with the utmost clarity. Some amateur astronomers have ventured beyond basic imaging to undertake more sophisticated observational techniques. Spectroscopy, once exclusively the purview of professional astronomy, has become attainable for advanced amateurs possessing specialized equipment. A limited number of observers have acquired low-resolution spectra of Three-Eye Atlas, identifying emission lines indicative of carbon compounds within its coma. While these amateur-generated spectra will not supersede professional observations conducted by instruments such as the James Webb Space Telescope, they nevertheless demonstrate the potential achievable through dedication and modestly priced equipment. The acquired data is subsequently disseminated online, augmenting the collective understanding of the comet's chemical composition. Photometry, the precise measurement of brightness, represents another domain where amateurs are making significant contributions. By meticulously measuring the comet's magnitude over successive nights, observers can track variations in brightness that may signify rotational anomalies within the nucleus or shifts in outgassing activity. Professional astronomical observation offers unparalleled precision, yet the contributions of amateur astronomers are invaluable for achieving comprehensive temporal coverage that would otherwise be unattainable. A coordinated collective of amateur photometrists can meticulously track the comet every clear night from diverse global vantage points, thereby constructing an uninterrupted light curve that effectively captures fleeting variations. Many enthusiasts have recounted their experiences observing the Three Atlas comet as profoundly humbling and equally awe-inspiring. One dedicated individual shared their account of setting up their telescope at 4:30 in the morning, their hands growing numb with cold as they watched their exhalations manifest as clouds within the beam of their red headlamp. Upon the comet's eventual appearance in the eyepiece, precisely as predicted by the ephemeris, they described experiencing a profound sense of connection across billions of years and unfathomable distances. That ethereal patch of light was, in fact, material originating from a stellar system predating Earth, which had traversed the vast expanse of the void to materialize in their telescope on that specific morning. Another observer detailed the challenge of explaining their pre-dawn vigil in freezing temperatures, pointing a tube towards the heavens to curious neighbors. After allowing them to view the comet through the eyepiece and elucidating its nature, the neighbor paused in silent contemplation before remarking, "We're truly not alone, are we?" This powerful sense of perspective, of comprehending Earth as a solitary world within a galaxy teeming with planetary systems, resonates deeply when encountering an interstellar traveler. The upcoming weeks represent a prime opportunity for amateur astronomical endeavors. As the Three Atlas approaches its closest proximity to Earth on December 19th, it will be advantageously positioned in the pre-dawn sky for observers in the Northern Hemisphere. Concurrently, the Moon will be transitioning to its new phase in mid-December, promising skies free from its illuminating influence. Furthermore, should the comet continue its observed brightening trend, a possibility suggested by certain data, it could become even more accessible to instruments of smaller caliber and perhaps even powerful binoculars. This is the very moment amateur astronomers have eagerly anticipated since the comet's discovery in July. Beyond the technical merits and scientific contributions, there exists a profound significance in the democratization of this celestial spectacle. The 3 Atlas is not sequestered behind proprietary data or exclusively within reach of those affiliated with major observatories. It is readily available to anyone willing to rise early, orient their telescope eastward, and direct their gaze upwards. This inherent inclusivity, this universal accessibility to cosmic observation for any sufficiently curious individual, is the very engine that sustains amateur astronomy amidst an era of automated surveys and sophisticated space telescopes. The comet itself makes no inquiry into credentials before reflecting sunlight into an observer's optics. It simply exists, visible to all, serving as a potent reminder that the cosmos belongs to every soul that looks skyward. The escalating brilliance of a celestial enigma, the reasons behind 3 Atlas's defiance of predictions. Something extraordinary transpired. While concealed behind the sun, the 3 Atlas comet experienced a significant increase in brightness. This was not merely the typical luminosity surge expected as comets approach perihelion, but rather a brightness that surpassed all projections, every model, and every expectation derived from decades of cometary scientific understanding. Astronomers analyzing the incoming data from space-based observatories found themselves confronted with an perplexing puzzle, devoid of an immediate solution. The narrative commences with instruments not primarily designed for cometary study. The Solar Terrestrial Relations Observatory, known as STEREO, comprises a pair of spacecraft tasked with monitoring solar activity and space weather. The Solar and Heliospheric Observatory, SOHO, focuses on detecting coronal mass ejections and other solar phenomena. The GEO-19 weather satellite is dedicated to tracking atmospheric and magnetic field conditions relevant to Earth. These instruments maintain a constant vigil on the Sun, and when 3 Atlas traversed their fields of view during late September and October, they captured a remarkable event. Chichang Zhang of Lowell Observatory and Carl Batoms from the U.S. Naval Research Laboratory meticulously analyzed this data, subsequently publishing their findings in a preprint paper uploaded to the ARF server. Their conclusions were striking. 3 Atlas exhibited a rapid brightening as it approached perihelion, at a rate that far exceeded that observed in typical Oort cloud comets at comparable distances from the Sun. The luminosity scaled inversely with the distance from the Sun raised to the power of -7.5, plus or minus 1. For perspective, most comets display an inverse relationship to the power of -2 to -4. A rate of 7.5 is indeed extraordinary. While the paper's language is carefully calibrated, as befits scientific discourse, the implications are unmistakable. The precise reason for 3 Atlas's accelerated brightening, which so dramatically outpaces that of most Oort cloud comets at similar radial distances, remains elusive. This singular sentence, embedded within technical analysis and observational data, represents one of the foremost enigmas presented by this interstellar visitor. Let us deconstruct the significance of this rapid luminosity increase. As a comet journeys closer to the Sun, solar radiation heats its surface, inducing the direct transition of solid material into gas, a process known as sublimation, bypassing the liquid phase. This release of gas forms the coma, the diffuse atmosphere surrounding the nucleus, and frequently generates tails of gas and dust that extend away from the Sun. The proximity to the Sun directly correlates with the intensity of heating, the vigor of gas release, and consequently, the comet's brightness. This established pattern is well understood through extensive observation and modeling. However, 3 Atlas brightened at a pace exceeding anticipated norms. The rate at which its luminosity surged suggested an unusual phenomenon was at play. This could indicate either a composition vastly different from that of typical solar system comets, or unique structural or behavioral characteristics, or a combination of both. In their paper, Jiang and Batams put forth several plausible explanations, each carrying intriguing implications. The initial hypothesis considers the velocity at which 3 Atlas is approaching the Sun. The comet is moving at a considerable speed, approximately 137,000 miles per hour, significantly faster than most comets originating from the Oort cloud, and indeed faster than either of the 2 previously identified interstellar visitors. This elevated velocity implies that the heating effect of solar radiation occurs at an accelerated rate, potentially initiating outgassing processes at a different tempo than experienced by slower-moving celestial bodies. It is conceivable that the fundamental physics governing cometary activation undergoes alteration when an object traverses the inner solar system at interstellar velocities. The second proposed explanation pertains to the comet's intrinsic composition. 3 Atlas may possess unusual characteristics within its nucleus related to its composition, morphology, or internal structure, acquired either within its home star system billions of years ago or during its extensive journey through interstellar space. Should the relative proportions of various volatile ices differ from those found in solar system comets, its outgassing behavior could be fundamentally distinct. Consider, for instance, a comet with an unusually high concentration of carbon dioxide compared to water ice. Carbon dioxide sublimes at considerably lower temperatures than water ice, meaning it begins to outgas at greater distances from the Sun. This early sublimation can generate a cooling effect that initially retards the sublimation of water ice, only for it to be released abruptly once the comet reaches a critical temperature, triggering a surge in brightness. Indeed, observations from the James Webb Space Telescope and other instruments have confirmed that 3IE Atlas is exceptionally rich in carbon dioxide when contrasted with most known solar system comets. Webb's observations conducted on August 6th revealed the comet's luminous condensed coma and indicated that carbon dioxide constituted the dominant component of its gaseous emissions, with water and carbon monoxide also present, albeit in proportions differing from typical observations. This chemical signature points towards a planetary system environment dissimilar to our own, potentially originating from a molecular cloud with unique elemental and compound abundances. The third facet of this brightening enigma involves variations in color. Jiang and Batams noted that colorimetric measurements indicated 3 Atlas appeared distinctly bluer than the Sun in proximity to its perihelion. This observation is genuinely surprising. Dust particles typically scatter sunlight, akin to how Earth's atmosphere renders sunsets red. The surface of 3 Atlas, being substantially cooler than the Sun's photosphere, should logically also produce reddish reflected light. Yet the comet appeared blue. Blue coloration in comets typically signifies emissions from gases rather than reflected sunlight. Certain molecules, when energized by solar radiation, emit light at characteristic wavelengths, many of which fall within the blue spectrum. Ionized carbon monoxide, for example, produces blue emissions. The observation that 3 Atlas appeared blue suggests that gaseous emissions contributed significantly to the comet's visible luminosity near perihelion, rather than solely reflected sunlight from dust. This aligns with the accelerated brightening phenomenon, where increased gas production leads to both the surge in luminosity and the blue hue. However, this is where matters become particularly intriguing from a more speculative viewpoint. Avi Loeb, known for his willingness to explore unconventional interpretations, published an analysis suggesting that the blue coloration could potentially be attributable to artificial sources. A hot engine or a source of manufactured light would indeed produce blue emissions. He promptly clarified that natural processes, particularly ionized molecules within the coma, could also account for the color, but the mere mention of artificial origins generated considerable attention. Loeb has consistently maintained that 3 Atlas ranks highly on his assessment scale for objects warranting thorough investigation for potential technological origins, and the brightening anomaly, coupled with its blue color, adds to his list of unexplained characteristics. The scientific community's reception to the brightening data has been varied. Some researchers interpret it as evidence that interstellar comets may possess intrinsically different compositions compared to their solar system counterparts, reflecting distinct formation environments around other stars. Each planetary system coalesces within a unique molecular cloud, possessing specific elemental abundances. The comets of our solar system offer insights into the cloud from which our sun originated approximately 4.6 billion years ago. 3I Atlas, potentially between 7 and 11 billion years old, formed in an entirely different milieu, possibly around a star that has long since ceased to exist. Its chemical makeup, therefore, should logically differ. Conversely, other scientists urge caution against overemphasizing preliminary data. While invaluable for observing objects near the Sun, space-based coronagraphs are not optimized for precise photometric measurements of comets. The brightness estimations carry inherent uncertainties. Furthermore, the predictive models for cometary brightening are predominantly based on Oort cloud comets, which themselves exhibit substantial variability in their behavior. It is possible that 3 Atlas simply represents an extreme outlier within the natural spectrum of cometary behavior. More data is required before definitive conclusions can be established. The paper authored by Zhang and Batams explicitly acknowledges this uncertainty. In the absence of a firmly established physical explanation, the future trajectory of 3 Atlas's post-perihelion behavior remains uncertain. Both a plateau in brightness or even a brief continuation of its pre-perihelion brightening appear as plausible outcomes as does a rapid fading subsequent to perihelion. In essence, the precise course of events remains unknown. The comet could maintain its current luminosity, continue to brighten for a period, or diminish in brilliance rapidly now that it is receding from the Sun. Each potential outcome would provide valuable clues regarding the underlying causes of the anomalous brightening. This juncture underscores the critical importance of the ongoing observational campaign. Ground-based telescopes, now that 3 Atlas has re-emerged from behind the Sun, are equipped to monitor its brightness evolution with significantly greater accuracy than the solar observatories in space could achieve during its perihelion passage. Should the comet persist in exhibiting unusual brightness characteristics, it would strengthen the argument that a truly anomalous phenomenon is unfolding. Conversely, if it settles into more typical cometary behavior, it would suggest that the rapid brightening was a transient phase, possibly linked to the sublimation of specific ices near perihelion. One hypothesis that has garnered considerable support involves the concept of delayed water ice activation. Carbon dioxide readily sublimes, initiating this process at distances of several astronomical units from the Sun. This sublimation results in evaporative cooling, analogous to how perspiration cools human skin. This cooling effect can effectively suppress the sublimation of water ice, maintaining its frozen state. Even as the comet draws nearer to the Sun, the solar heating eventually overwhelms this cooling mechanism. When water ice subsequently begins to sublimate in substantial quantities, the comet experiences a dramatic surge in brightness. This scenario could account for both the rapid brightening and its unexpected timing. Supporting this hypothesis is data from the Spherex spacecraft, which observed 3 Atlas in August. Those observations revealed a carbon dioxide plume extending approximately 348,000 kilometers from the nucleus, an immense distance indicative of vigorous carbon dioxide outgassing. If this gas was indeed exerting a cooling influence, it might have kept the water ice dormant until perihelion, when the solar heating became intense enough to trigger widespread water ice sublimation. The detection of water by NASA's Neil Gehrels Swift Observatory adds another crucial piece to this complex puzzle. The Swift telescope, trained on 3 Atlas, identified hydroxyl gas, a chemical indicator of water. Hydroxyl is generated when water molecules are dissociated by solar radiation. This detection confirms the presence and activity of water within the comet's coma. The pertinent question is whether the activation of water increased abruptly near perihelion, contributing to the brightness surge, or if it has been a more uniform process throughout the comet's approach. Spectroscopic observations in the coming weeks are poised to provide answers to these questions. By analyzing the specific wavelengths of light emanating from 3 Atlas, astronomers can identify the molecules present in the coma and their respective abundances. If water emissions are observed to increase dramatically compared to earlier observations, it would bolster the delayed activation hypothesis. Conversely, if carbon dioxide remains the dominant constituent even at this stage, it would suggest an alternative explanation for the observed brightening. The brightening enigma also carries implications for mass loss. Loeb has calculated that if the rapid brightening resulted from substantial outgassing, 3 Atlas may have shed a significant portion of its mass during perihelion, potentially as much as 10%. Such substantial mass loss should manifest as a substantial debris cloud surrounding the comet in the ensuing months. The European Space Agency's JUICE spacecraft, scheduled to observe 3 Atlas in November, may be the first to detect this debris field, should it exist. The data from these observations will not reach Earth until February due to transmission delays, but they will furnish critical information regarding the comet's post-perihelion state. If 3IE Atlas did indeed lose 10% of its mass, this would equate to the evaporation of a surface layer averaging 4 centimeters in thickness across the entire nucleus. For an object estimated to range between 440 meters and 5.6 kilometers in diameter, this represents a considerable quantity of material. The absence of such a discernible debris field would suggest that the brightening was not primarily driven by conventional cometary outgassing, thereby opening avenues for more unconventional explanations. The brightening mystery exemplifies science in action, where unexpected observations are confronted and efforts are made to formulate explanatory frameworks. Every hypothesis generated yields predictions that can be rigorously tested through subsequent observations. The scientific method does not demand immediate comprehension of every observed phenomenon. Rather, it mandates the acknowledgement of what remains unknown and a systematic approach to its elucidation. 3 Atlas has presented astronomers with a genuinely perplexing subject for investigation. And the resolution of this enigma, whatever its ultimate nature may prove to be, will undoubtedly advance our understanding of comets, interstellar objects, or potentially both. December approach, the final opportunity before Jupiter and beyond. December 19th, 2025. Mark that date. On this day, 3I Atlas will achieve its closest approach to Earth, passing at an approximate distance of 269 million kilometers, equivalent to about 1.8 astronomical units. This marks the concluding significant observation window before the comet continues its trajectory toward Jupiter and subsequently departs our solar system permanently. Every available telescope capable of being directed towards the comet will be actively engaged. Every instrument equipped to gather data will be deployed. This is it, the last chance. However, the narrative does not commence on December 19th. It is unfolding presently, building momentum throughout November and into the early days of December. As the geometric alignment becomes increasingly favorable, the comet ascends higher each passing morning. Its altitude above the eastern horizon for observers in the northern hemisphere escalates daily, offering darker backgrounds and extended observation periods before the encroaching twilight obscures the sky. By early December, 3 Atlas will be optimally positioned for extended imaging sessions, rising several hours prior to sunrise. The lunar phases are remarkably cooperative. The new moon on December 1st provides pristine dark sky conditions, precisely as the comet reaches its optimal altitude throughout the initial 2 weeks of December. The moon remains either new or in a slender crescent phase, rising shortly before the sun and contributing minimal light pollution to the pre-dawn firmament. Observers will not face the challenge of a luminous moon overwhelming the comet's faint glow. Nature has conspired to provide perfect viewing conditions for the culmination of this celestial visitation. Professional observatories are coordinating their efforts to maximize data acquisition during this critical period. The Hubble Space Telescope, which captured detailed imagery of 3 Atlas back in July, when the comet was 277 million miles from Earth, is scheduled for additional observations in December at a closer range. With the comet potentially still exhibiting activity from its recent perihelion passage, Hubble should be capable of resolving the coma's structure with unprecedented detail, possibly even revealing the nucleus itself should the surrounding dust have sufficiently dispersed. The James Webb Space Telescope, leveraging its near-infrared capabilities, will continue its spectroscopic observations to track the evolution of the comet's composition and activity as it recedes from the Sun. Webb's earlier observations in August detected carbon dioxide, water, and carbon monoxide within the coma. Follow-up observations in December will ascertain whether these abundances have changed, if new molecules have appeared as different ices undergo sublimation, and whether the anomalous carbon dioxide dominance persists or shifts towards more conventional cometary chemistry. Ground-based observatories worldwide are allocating valuable observation time to 3 Atlas. The Gemini telescopes, both the northern facility in Hawaii and the southern one in Chile, have scheduled observations employing multiple instruments. The Keck Observatory in Hawaii, which provided earlier spectroscopic data revealing puzzling nickel emissions without corresponding iron signatures, will continue its monitoring of the comet's chemical composition. The Very Large Telescope in Chile, equipped with powerful spectroscopic instruments, will analyze the coma's structure and composition across various wavelengths concurrently. Radio telescopes are also actively listening. While 3 Atlas itself is not a radio source, radio observations can detect specific molecules within the coma through their characteristic emission lines. The Atacama Large Millimeter Array, ALMA, with its exceptional sensitivity, may detect rare molecules that optical telescopes are unable to observe. These measurements would offer profound insights into the comet's chemical inventory, revealing compounds that originated in its home star system billions of years ago and have remained perpetually frozen ever since. The December approach also represents a crucial proving ground for several hypotheses concerning 3 Atlas. If the comet experienced substantial material loss during perihelion, as suggested by certain models predicated on its rapid brightening, December observations should reveal a significant debris cloud. This cloud, by scattering sunlight, would appear as an expanded halo enveloping the nucleus. The extent and configuration of this dispersed material would furnish direct proof of the volume of matter ejected and the intensity of the event. Conversely, the absence of a substantial cloud of debris would indicate that the brightening was not predominantly due to typical cometary outgassing, necessitating alternative hypotheses. The issue of acceleration not governed by gravity will become verifiable during its December transit. David Farroya of NASA's Jet Propulsion Laboratory reported the detection of non-gravitational acceleration at perihelion, encompassing both radial and tangential components. This acceleration, if attributable to outgassing, ought to result in a predictable alteration of its path. Precise astronomical measurements in December, involving the meticulous tracking of the comet's exact position against the backdrop of stars, will reveal whether its trajectory aligns with predictions based on the measured acceleration or if other forces are at play. Any deviation would be of considerable importance. For amateur astronomers, December signifies the culmination of many months of eager anticipation. The comet will achieve its most brilliant apparent magnitude since its initial discovery, potentially reaching magnitude 8, or even exceeding that if activity persists post-perihelion. At magnitude 8, Comet 3I Atlas will be observable through binoculars under reasonably dark skies, no longer exclusively requiring telescopes. For casual observers willing to rise before dawn and consult a star chart to locate the comet, this could represent their sole opportunity to witness an object from beyond our solar system with their naked eyes, or at least with minimal optical assistance. The period of visibility extends through the latter part of December and into early January of 2026. Although the comet will be diminishing in brightness by then as it recedes from both the Sun and Earth. Scientific interest will remain keen even as the comet fades, as each additional piece of data helps refine models of its composition and behavior. However, for the majority of observers, December is the pivotal moment, with the comet at its nearest, brightest, and most accessible. Following December, Comet 3I Atlas will continue on its hyperbolic trajectory away from the inner solar system. Its next significant celestial encounter is scheduled with Jupiter on March 16, 2026. The comet will pass at an approximate distance of 53 million kilometers from the colossal planet, close enough that Jupiter's potent magnetic field and radiation belts could potentially influence the comet's coma or even subtly alter its trajectory. NASA's Juno spacecraft, currently in orbit around Jupiter, might have the capability to observe Comet 3I Atlas during this flyby, although the approval of a mission extension for this specific purpose remains uncertain, despite the advocacy of Congresswoman Luna. Observations of Jupiter would be valuable for several reasons. Firstly, the comet will be in a different physical state compared to its Mars flyby or the December Earth observations. By March, it will have significantly distanced itself from the Sun, and its level of activity should have correspondingly changed. Secondly, Jupiter's environment is unique, possessing powerful radiation and a strong magnetic field that could interact with the comet's coma in observable ways. Thirdly, this represents the final plausible opportunity for spacecraft observations before Comet 3I Atlas departs the solar system. Beyond Jupiter, Comet 3I Atlas will proceed towards the outer solar system and eventually re-enter interstellar space. Its journey will take it past the orbital paths of Saturn, Uranus, and Neptune over the ensuing years, though the comet will be far too faint for observation by that time. Eventually, perhaps a few years from now, Comet 3I Atlas will cross the heliopause, the boundary where the solar wind yields to the interstellar medium, once again becoming an interstellar object traversing the galaxy. Its ultimate destination remains unknown. It is conceivable that in millions of years it might transit another star system, affording alien astronomers, should they exist, a similar observational opportunity to the one we have now. The December observations carry philosophical significance beyond their scientific merit. This is humanity's chance to examine material originating from another star system up close, or as close as we are likely to get within our lifetimes. The comet contains information pertaining to stellar and planetary formation processes that occurred billions of years before the existence of our Sun. Its chemical makeup reflects the molecular cloud where it originated, providing a snapshot of galactic chemistry from an earlier era. Every spectrum, every image, and every measurement contributes to our understanding of how planets and comets form around other stars. Yet, there is also a certain poignancy in its finality. Comet 3I Atlas is not orbiting the Sun. It is not returning. This is a singular visit, and once the comet departs, the opportunity to study it will be lost forever. No future mission can pursue it, and no technological advancement within our lifetimes will bring it back within the reach of our instruments. December marks both a climax and a conclusion, the peak of observational potential, followed by a prolonged farewell as the comet recedes from our telescopes and retreats into the darkness between stars. The data gathered during December will serve as a foundation for research for years to come. Cometary scientists will meticulously analyze images, searching for subtle intricacies in the coma's structure. Spectroscopists will extract every possible molecular identification from the spectral data, compiling a comprehensive chemical inventory. Dynamicists will refine trajectory calculations, potentially tracing the comet's path backward through the galaxy to estimate its point of origin. Even if a specific home star system cannot be identified, its trajectory will reveal the direction from which it arrived in the galaxy. These trajectory calculations are fascinating in their own right. Comet 3I Atlas entered our solar system with a distinct velocity and direction. By carefully measuring its path and accounting for gravitational influences from the Sun and planets, astronomers can ascertain the comet's velocity relative to the local standard of rest, which is essentially the average motion of stars in our galactic vicinity. This velocity vector, coupled with the direction from which the comet arrived, offers insights into its origin. Did it originate from a nearby system, perhaps passing through a stellar neighborhood only a few light years away? Or has it been journeying through interstellar space for millions of years, covering vast distances from some remote region of the galaxy? The uncertainties inherent in these calculations are substantial. Minor errors in positional velocity measurements can amplify over the immense timescales and distances involved when tracing trajectories backward. Even minute gravitational perturbations from passing stars during the comet's interstellar voyage would unpredictably alter its path. Nevertheless, the endeavor is worthwhile, as even broad estimations of its origin hold significant scientific value. At the very least, its trajectory provides information about the density and kinematics of interstellar comets, and how numerous they might be drifting through the galaxy at any given time. Recent studies suggest that interstellar visitors like Comet 3I Atlas may be more prevalent than previously believed. In fact, statistical analyses indicate that there is almost always one within our solar system at any given moment, although most are too small or too distant from the Sun to be detected. Comet 3I Atlas is visible because it became active, developing a coma that rendered it far brighter than its inert nucleus alone would be. How many dark, inactive interstellar objects have passed through undetected? We can only make estimations based on the few we have encountered. This realization offers a new perspective. Our solar system is not an isolated entity. The space between planets is continuously traversed by objects originating from elsewhere in the galaxy. Most pass through unnoticed, remaining dark and cold, but occasionally one ventures close enough to the Sun to become active, sublimating volatile materials and becoming visible, thus presenting us with this precious opportunity to study matter from beyond our stellar neighborhood. Comet 3I Atlas is not an anomaly. It is simply the most recent visitor that we have managed to capture and thoroughly observe. December 19th approaches with a palpable sense of urgency within the astronomical community. Proposals for telescope time are in fierce competition. Researchers are meticulously coordinating their schedules to ensure they do not miss crucial observing windows, and data processing systems are being prepared to handle the anticipated influx of observations from instruments located across the globe and in space. This is the nature of astronomical campaigns when the target is ephemeral and the stakes are high. For those of us observing from the periphery, whether as amateur astronomers capturing our own images or as interested followers absorbing each new discovery, December offers a chance to be part of this moment of cosmic communion. The comet is indifferent to our observation. It follows its trajectory dictated by physical laws that were in operation before life existed on Earth and will continue to operate long after our sun has ceased to exist. However, we care. We gaze upwards and perceive meaning in that faint smudge of light, a visitor from the vastness of space and time, present for a fleeting moment before continuing its eternal journey through the galaxy. The December approach is not truly an end, rather it is a transition. It marks the point of closest passage before Comet 3I Atlas embarks on its lengthy retreat into obscurity. The data collected will undergo years of analysis, papers will be published, conferences will feature debates on interpretations, and our comprehension of interstellar comets will deepen. However, the direct experience of observation, the act of directing our telescopes towards this visitor and collecting its reflected sunlight, photon by photon, reaches its zenith in December. It is a moment to be cherished, documented, and remembered, for opportunities of this magnitude are rare in human lifetimes. The next interstellar comet might not arrive for many years or even decades, and when it does, it will be a distinct object with its own unique enigmas to unravel. Comet 3I Atlas is singular, and December 2025 is our allotted time with it, the final opportunity before it vanishes into the immense dark ocean of space, where it has spent billions of years and will continue to spend billions more.